In today's video, we're going to talk about energy changes. Remember in our past video, we talked about how we know a chemical reaction has happened when we see some form, when we feel it getting hot or cold, or we see some light being produced, okay? That's what we talk about when we talk about energy changes. When a chemical reaction happens, remember that bonds have to be broken and new bonds have to be formed, okay? So new substances are formed and a chemical reaction is said to have taken place when we have a chemical change. Okay, now when we talk about the reaction itself, like the actual chemicals involved in the reaction, that is what we refer to as the system. Okay, so the particles, the actual atoms themselves are the system. Everything else, if it's taking place in, let's say, a beaker filled with water, then the water, the beaker, your hand, the air, whatever, everything else around the system is what's called the surroundings, okay? So the reaction itself is called the system, and then everything else that's could possibly touch or be a part of that is part of the what call the surroundings, okay? Now, when that chemical reaction happens, if that chemical reaction gives off energy, so energy is released, that energy goes from the system to the surroundings as shown here. And when that happens, that is called an exothermic reaction. I think of it as the heat or the energy is exiting the system, okay? And when that happens, when energy is released, it's heating up the water, the beaker, your hand when you touch it, and you go, ooh, that feels warm. Okay, that is an exothermic process. Okay, if the reaction itself needs some energy, and it's taking some energy from the surroundings, okay, that is referred to as an endothermic reaction or an endothermic process. Okay, and that means it's taking heat from the water, from the glass of the beaker, and from your hand as you're touching it, and you go, ooh, that feels cold. Well, why does it feel cold? Because it's taking energy from you and from the beaker and from the water to make that reaction happen. Okay, so, and again, I think of that as the heat or the energy is going, we call it endothermic. I think of it as the heat going into, like into kind of the system. So the heat is exiting the system or the heat is going into the system is the difference between exothermic and endothermic. Okay, now if the temperature of the surroundings is monitored, we find that in the case of an exothermic reaction, the temperature of the surroundings goes up. That makes sense because the heat is being released. Now, let's talk about how that happens. Okay, in every chemical reaction, remember there's two parts. There's a part where there's always going to be a part at the beginning that it's going to take energy to break those bonds. Okay, and so the difference, so here's the reactants, and then we go all the way up to here. Okay, and that rise, that is the part where this is absolutely the endothermic part of that process. Okay, every time you break a bond, it requires energy. There's some confusion about that in some parts of the science world, but every time you break a bond, it is an endothermic process. So notice that at the beginning of every reaction, there is an endothermic part, okay? And again, that endothermic part is the bonds in the reactants breaking. Okay, think about when you light your barbecue, and what do you need to light that barbecue? You use a lighter, or sometimes you use a match, or sometimes you push a button. Okay, you have to provide some energy to start breaking those bonds, okay? So this energy from here, right here, or right here is called the activation energy. And we're going to get into this in more detail in Unit 5. We're going to talk about energy a little bit more, but this is just kind of a good introduction. So every reaction has that activation energy that you have to overcome in order for that reaction to happen. Okay, because again, you have to break those bonds at the beginning. Now, once you get to this point right here, sometimes this point is called the activated complex. You're kind of in between the reactants and the products, but you've broken all of those reactant bonds that are going to break. Well, now you start to release the energy, and now you start to release the energy here. And this part right here is now the exothermic part. Okay, now you'll notice here in these two different energy diagrams that overall, this one here on the left is endothermic. Now, why is that? This is endothermic. Why is that? Because you can see the amount of energy it took to break those bonds is more than the amount of energy that was released when the new bonds were formed. Okay, which basically means the activation energy was high enough that the amount of energy released when the new bonds were formed was not enough. Okay, so overall, this is a process that's going to require energy. That's the one that's going to feel cold. Okay, this one though, notice that the amount of energy it took to break the bonds, the activation energy, and the amount of energy that was released when the new bonds were formed, it's way, way more the amount of energy that was released when the new bonds were formed. Okay, and so overall, that's an exothermic process. Okay, so let's look at what it says here. In order to get the products to a higher energy than the reactants, energy must be absorbed from the surroundings. And again, as that happens, the temperature of the surroundings, the water, the beaker, your hand, the air, goes down. Okay, in this case, though, in order to get the products to a lower energy than the reactants, energy is released as all of this is happening here, as those new bonds are formed, and the temperature of the surroundings goes up. Okay, so in other words, in an endothermic process, heat is transferred from the surroundings to the system. Okay, think of two solutions being poured together and a reaction occurring. The water in this case is the surroundings, and the reaction itself is the system. So in an endothermic process, the heat is transferring from the water to the reaction to allow the reaction to happen, and therefore when you touch that, it feels cold. Okay, in an endothermic process, we can say that the energy, or we're going to talk about this later, the enthalpy of the products is higher or greater than the enthalpy or the energy of the reactants. In an exothermic process, the energy or enthalpy of the products is lower than the energy or enthalpy of the reactants. Okay. In an exothermic process, obviously the opposite occurs. Heat is transferred to the surroundings. It feels hot, and the energy of the products is lower than the energy of the reactants. Okay. Again, in order for any reaction to begin, whether it's exothermic or endothermic, though, you do have what's called an activation energy barrier. If you can't give the reaction enough energy to overcome this initial energy, this is a barrier. It's like rolling a ball up a hill. If you don't roll that ball hard enough, it's not going to make it over the top. Okay, if it makes it up to here, what's going to happen? Of course, it's going to roll back down. Okay, same thing. If there's not enough energy to give that reaction enough energy for that reaction to start, it can't and it won't. Okay, and that's why a lot of reactions simply don't happen, because if you can't overcome this barrier here to break those initial bonds, then the reaction simply won't happen. Okay, and again, we're going to talk about activation energy later. That was just kind of an introduction to energy. And again, even though there's not going to be any questions in your homework packet about this, this is something you absolutely should be familiar with. You can probably expect some type of diagram like these on your test. So let's just look at a few questions, because these are some of the things that throw kids off. So example number 1, is the boiling of water an endothermic or an exothermic process? Justify your answer. So here's where you start to get things mixed up in your head, because you're like, oh, well, boiling water, that feels hot. Oh, well, if it feels hot, then it must be exothermic. Okay, why is boiling water hot? Because you heated it up, because you turned the stove on or you lit the fire, and you're adding heat to that water, and that water is absorbing that heat, and that allows the water to break into a gas. So therefore, the boiling of water is absolutely endothermic. Okay, basically, anytime you go from a solid to a liquid or a liquid to a gas, you have to absorb energy to do that. Okay, so in this case, you're going from water to liquid water to a gas. Okay, those are always an endothermic process. Okay, and the opposite is also true. Okay, is the condensation of water vapor an endothermic or exothermic process? Anytime you go from a gas to a liquid or a liquid to a solid, that is an exothermic process. It has to get rid of some of that energy in order for it to reform back into a liquid. That's backwards. No, sorry, that's right. Or, yeah, to go from a gas to a liquid or a liquid back to a solid. Okay, so that is an exothermic process. Okay, let's come back up here to example 1. In order for water to break apart, you have to give it some energy. Okay, that's why on a hot day, the pool evaporates more than on a cold day. Because when you add some energy to that, adding energy, it's absorbing that energy. Remember, that's an endothermic process, is it's getting absorbed. As it's getting absorbed, it's allowing those molecules to have more energy and they can break off from each other. Okay, that's an endothermic process. The problem with boiling water is you think, oh, it's hot, it has to be exothermic. The reason it's hot is because you heated it up. Okay, an exothermic process is a process that releases its own heat. It gives off heat. Okay, boiling water is not giving off heat. You're adding heat to the water. And again, it's absorbing that heat. That is endothermic. Okay, number 3, which type of reaction is generally more, you're going to see this term a lot later on, which type of reaction is generally more thermodynamically favorable? Which one's more likely to occur, exothermic or endothermic? Well, think about it in terms of, look at those curves back up here. In an endothermic reaction, what happens if it's really, really cold? Well, it may not have enough energy to overcome that barrier. It's going to give off a little bit of energy, which will kind of help keep that reaction going, but not enough. In an exothermic process, yeah, you need a little bit of energy to start it. But once that reaction starts, now you're producing enough energy to keep providing enough activation energy to keep this reaction going. Okay, think about like when you light your barbecue. Lighting a combustion reaction is absolutely an exothermic process. Okay, and the energy that is released as those new products are formed is enough energy to provide the activation energy for the new molecules coming in to have enough energy to keep that reaction going. And so that reaction literally will continue forever until you turn off the gas or you run out of oxygen, which could be trouble. Okay, but in an endothermic process, if you don't have enough heat to keep this going, then that reaction will stop. Okay, so which one is more likely to occur? Absolutely an exothermic process. And why is that? Because it releases enough energy to provide the activation energy for that reaction to keep going forever. Okay, so here's another example here. It says a reaction occurs where the concentration of the hydroxide ion is 0.50 molar. The reactions run again, but now with a concentration of hydroxide equal to 2 molar. Is the activation energy for the reaction when the concentration of OH, not sure what that is there, is 2 molar greater than, the same as, or less than the activation energy when the concentration of hydroxide is 0.5 molar? Justify your answer. Okay, and you should realize there that really the activation energy does not change in that case. Okay, it still takes as much energy to break those bonds, whether it's 0.5 molar or 2 molar, than if it's at a different temperature or something like that. So in this case, the activation energy is the same because activation energy does not change with concentration. Okay, a catalyst, which is something we'll talk about more in Unit 4, can cause the activation energy to change, okay, but a change in concentration does not. Okay, what if you change the temperature though? What if again, same situation here, what if you have 0.5 molar at 25 degrees Celsius and then at 40 degrees Celsius? Okay, does that cause the activation energy to change? No, it does not. Okay, a change in the temperature does not change the activation energy. When you change the temperature, what you're doing is you're giving the particles more energy, and so that means more of those particles can overcome the activation energy barrier. So by raising the temperature, we know that increases the kinetic energy, and then therefore more of those particles are now going to have enough energy to overcome this big activation energy barrier that we have here at the beginning. Okay? So a greater percentage of the particles will have enough energy to overcome that activation energy barrier.